Hello everyone. Today I want to discuss the one-way speed of light. In the last few years there have been quite a few videos published on this subject, and the first one that I saw was a video by Fizeau. It's a really great video, by the way, and if you haven't seen it, I would encourage you to go watch it. That particular video sparked a whole lot of so-called reaction videos, and I guess this is also one. It's pretty late to the party, but hopefully I can still add a few new insights. Apparently, the whole discussion on this subject originates from a paper published by Albert Einstein in 1905. In that paper, Einstein defines the speed of light as 2 times the distance between points A and B divided by the total time it takes for the light to cover the distance from A to B and back. So by doing this, Einstein specifically avoids any problems that are associated with defining a one-way speed of light. And based on this definition, he then builds the theory of special relativity. Now, I guess most of us assume that the speed of light is equal in both directions, but Einstein knew that this would be very difficult to prove experimentally. So the most common and maybe the only accurate way to measure the speed of light is by measuring the two-way speed of light. So you take 2 points A and B, which are separated by a known distance d. At A there is a light source and a detector, and in B we have a mirror. And we measure the time, delta t, it takes for the light originating from the source to travel from A to B and then return to A and be detected. And so this measurement gives us the speed of light in agreement with the convention by Einstein. The first one to perform this measurement with pretty good accuracy was Armand Hippolyte Fizeau. In 1849 he did this experiment where he pointed a light beam towards a mirror some 8.6 kilometers away on a mountain. He used a clever trick involving a fast spinning wheel with notches that could block both the outgoing and incoming beams, and he recorded at which rotation speeds the returning beam was either blocked or transmitted. This then allowed him to calculate the total time it took for the light to return, and from this the two-way speed of light. If you want to know more details about this experiment, I would encourage you to go watch a video made by Alpha Phoenix, where it's explained in a very clear and entertaining way. But this experiment measures the two-way speed of light, written as C2 in the schematic, to distinguish it from the one-way speed of light, C1 for the outgoing beam and C1- for the returning beam. So we can measure the two-way speed of light with high accuracy and not the one-way speed of light. But the question I had was, do we really need to measure the one-way speed of light to be certain of its value? What if we can prove that the speed of light must be identical in opposing directions, so that C1 is always equal to C1-? Then combining this knowledge with the formula for the two-way speed of light would automatically prove that both C1 and C1- are equal to the two-way speed of light C2. And this shifts the actual problem from can we measure the one-way speed of light to can we prove that the speed of light must be equal in opposing directions? So, is there maybe some sneaky way to directly compare the speed of light in both directions directly? Let me explain an idea I had about this in a bit more detail using a schematic. As the basis for the experiment, we'll use ultra-short laser pulses generated by, let's say, a femtosecond pulsed laser. Each individual laser pulse is split into 2 pulses using a beam splitter and then directed by several mirrors into a measurement setup from opposite directions. Our setup consists of 2 detectors in locations A and B, which are assigned dA and dB. So the 2 detectors are separated by a distance d and are both connected to a very accurate timing device. For convenience, the timing device is placed exactly halfway between the 2 detectors. The 2 detectors can not only measure the passing of a pulse, they can also distinguish between pulses coming from the left and from the right because they're built around a beam splitter. And in the upcoming images I've given the pulses 2 different colors just to distinguish between pulses coming from the left and from the right. Pulses from the left are indicated in green and those from the right are shown in red. Now, for the sake of simplicity, we'll just ignore any of the vertical distances shown in this schematic and we will just include the horizontal distances, and what we'll do is study the timing of pulses coming from both directions. The idea behind the setup is of course that by timing the arrival of light from both directions simultaneously, this could maybe allow us to compare the speed of light in both directions and somehow conclude that they must be the same. But just to be sure, before I put a lot of effort into building such a setup, let's first evaluate what we would actually measure. Okay, so these are the graphs of what we expect to measure with each detector at the central timing device as a function of time. Our clock in the middle registers a total of 4 pulses for each pulse originating from the laser, and we will just measure the order of the incoming pulses. So in this example measurement, we observe that the first pulse is detected by detector A and it's coming from the left. The next detection occurs at detector B and it detects a pulse coming from the right. These light pulses then travel in opposite directions towards the second detector, where they are again registered. In this case, first the pulse from the left by detector B, second the pulse from the right by detector A. And now you might say, okay, since all distances between the detectors and clock are identical, we can now just take the time elapsed between T1 and T3 and compare it with the value between T2 and T4. And if we find they are the same, then we have proven our point, because in that case C1 must be equal to C1 dash, right? Actually, no, it's not that simple, because it would take some time for the information about the arrival of the light pulses to travel from detector to clock. And since the fastest speed with which information can be transferred is the speed of light, the signal traveling from detector to clock can never exceed this speed. Okay, so no problem. Let's correct for this and assume for simplicity that the information about the arrival of the pulses at the detector can indeed be transported to the clock with the speed of light. And in that case, we can simply correct for the delays based on the distances between detectors and clock. Okay, so let's do this and calculate the times of the pulses actually being detected at detector A and B based on what we have measured at the clock. And these events at the detector will have occurred earlier in time because they have been delayed by a half times d divided by the speed of light. And we will assign the events at the detector as the real times of detection, displayed here as TR. Now, since we cannot assume that the values for the speed of light in the opposite directions C1 and C1 dash are the same, we can unfortunately also not assume that the delays are the same. But fortunately, we can calculate the exact values. So here's a list of the real times that a pulse arrives at a detector for each pulse registered by the clock. And as you can see, these have all been corrected for the respective delays occurring between detector and clock. Now, I want to go through these as quickly as I can because this is actually pretty boring stuff. But if you're interested and you need more time, just pause the video at any moment to take a closer look. Okay, so we also know that the difference between the real detection times for light going from A to B, so between TR1 and TR3, should be equal to the distance d divided by C1. And for TR2 and TR4 in the other direction, this value is d divided by C1 dash, so the speed of light from B to A. And this means that we have two additional equations to work with. And we can now combine all of these and examine what we measure at the clock exactly. And here is the result of combining all the 6 equations. Again, I'm not going through everything, I just want to direct your attention to the 2 resulting equations in the yellow boxes. And these describe what we measure for the timing of pulses going from A to B and those going from B to A. And it turns out that these are both equal to a half times d divided by C1 plus d divided by C1 dash. Okay, hold on, what does this mean? Well, it means that we can basically fill in any value for C1 and C1 dash and still observe an identical time delay in both directions. So the result turns out to be 2 identical measurements of the half value of the two-way speed of light. And so this taught us nothing about a one-way speed of light in a particular direction. Now you might say, okay, maybe this is just an unfortunate coincidence. What if we place our clock off-center, for example, at a quarter of the total distance from A? In that case, we can do the same evaluation and formulate a similar set of equations, which we can rewrite to evaluate the timings measured at the clock, and in this way arrive at the highlighted equations like the last time. Now it's interesting to see that the timings measured at the clock have actually changed quite significantly. But if you look at the values that we find for the time differences between pulses going from A to B and those from B to A, there's still a sum of equal contributions by C1 and C1 dash, so the speed of light in opposing directions. And so this measurement also reveals no information about a one-way speed of light in either direction, even though the pulses all originate from the same source and travel through the same space in opposite directions at the same time. So how can this be? Well, in retrospect, it's actually very simple. The experiment is just two unrelated two-way speed of light experiments. So let me quickly illustrate this using the second configuration where the timing device is located at a quarter of the distance. If you consider a light pulse coming from a specific direction, say from the left, you observe that the information related to the first detection and the light pulse arrive at the same time at the position of the clock. And what from that point on remains from the actual measurement is in fact a two-way speed of light measurement for 3/4 of the distance d, which is what our first equation tells us. For pulses from the right, we observe something similar. Here, the two-way speed of light measurement is for the remaining quarter of the distance, and so it turns out that the timing we observe is only dependent on the position of the clock with respect to the detectors, but never of a speed of light in one individual direction. Okay, it's clear by now that this path is actually a dead end, and sorry for wasting your time explaining this far-fetched and useless experiment. The main thing I took away from all this myself is that we cannot know anything about what happens in A and B until the information about the events reaches us. So this is the reason why we need to define the speed of light as a two-way thing, because it is basically the only value that we can actually measure. Now this could be the point where we give up, right? Where I say, okay, that's it for this video, thanks for watching, goodbye. No, not yet. Let's return again to the original question. Can we prove that the speed of light must be equal in opposing directions? This time we'll approach that question from a different angle by looking at the wave character of light. But before I continue, let me state that the next part of the video does by no means contain a scientific proof. I just try to formulate an intuitive explanation why the local speed of light cannot be different in opposing directions. Electromagnetic radiation, like visible light and radio waves, were until the beginning of the 20th century considered to be purely a wave phenomenon. And even today, if you want to calculate the properties of an electromagnetic field in a system, like its amplitude or intensity, the wave description of light is your best friend. For the wave description of light, we generally turn to the Maxwell equations. Now, there are many videos that explain these in great detail, so I'm not going to do that here. I just want to point out that these four equations together can describe the electric and magnetic fields in vacuum and how they relate to the presence of charge and current. The bottom two differential equations describe the electric and magnetic field propagation as a function of time. And if you take a closer look at the fourth formula, you can observe that it contains two constants, which are called permittivity and permeability. These two constants are basically properties of the vacuum and have actually been measured independent from each other. But not only are these two constants essential for calculating the correct temporal and spatial wave behavior of electromagnetic radiation, together they also describe the theoretical value for the propagation speed of light waves, and the value calculated in this way exactly matches the one we measure in our speed of light experiments. On top of that, the propagation speed in vacuum is completely independent of frequency. Now, in a sense, the Maxwell equations describe the vacuum as a medium that has elastic and inertial properties. The elastic properties of space are mainly found in the permittivity and describe how energy is stored in the electric field, and the inertial properties of space are present in the magnetic permeability, which represents how the vacuum resists changes in the electric field. It turns out there is a strong analogy between electromagnetic radiation propagating through space and the behavior of longitudinal waves propagating through a physical elastic material. As just stated, the propagation speed of light is determined by the permittivity and permeability of the medium, and in the case of waves propagating through a physical material, the velocity of propagation is determined by the ratio between a spring constant and an inertial density. Now, the reason why I want to show this analogy and use it here is that it's so much easier to intuitively understand wave propagation from a model consisting of springs and masses than define a medium by permittivity and permeability, which are rather abstract properties to most of us. Using the analogy, you can consider the vacuum to be an elastic medium with a very high stiffness to inertia ratio. The constant that relates the two here is equal to 1 divided by the permittivity times the permeability of space. And this follows simply from recombining the two formulas for wave propagation. Now, of course, this still is just an analogy, and maybe a more accurate way to look at the stiffness to inertia ratio of space is to say that the rate at which energy is transported through space is very high compared to the value of its actual energy density, also called the vacuum energy. In the simplified model used here, the vacuum is an elastic medium and it is visualized by a network of identical balls and springs. The balls represent the inertial properties of space and the springs represent the elastic properties of space. If the vacuum is isotropic, this means that the spring constant and inertial density should be the same everywhere, and so wave energy will spread out equally fast in all directions. This simulation is of course a 2D simplification, but here you can see what happens in such a system if we supply energy to the medium in the form of a local harmonic oscillation. So this is the type of behavior that we expect in a spatially and directionally isotropic medium. In order for the speed of light to be dependent on direction, we need to introduce some kind of anisotropy in the elastic properties of space. You could think, for example, of an elastic medium that has a uniform inertial density, but contains a different spring constant along the x and y axis. And we can simulate the wave behavior resulting from this directional elastic anisotropy. It results in an anisotropic wave propagation speed. In fact, this type of anisotropic behavior can be observed for light in certain physical materials, such as for example sapphire and lithium niobate, where the effective speed of light is different along different crystal axes. But as is clear from both the schematic representation and the simulation, the wave propagation speed will still be identical in opposing directions. So this type of anisotropy cannot explain how the propagation speed could be different like in a two-way speed of light experiment. Let's consider yet another type of medium, one that is only spatially anisotropic. In this schematic example, the anisotropy gradient is a function of position in the x direction, where the speed of wave propagation decreases from left to right. If we want to implement this type of anisotropy using balls and springs, we can, for example, do this by introducing a gradient in the value of the spring constant k as a function of x coordinate. So let's quickly simulate a situation where space contains a wave propagation speed with this gradient. Here are two wave sources placed in A and B, emitting waves in opposite directions. We observe that the waves from the left start out moving fast and from the right moving slow, but eventually they need exactly the same amount of time to get to the other side. Now notice what happens after they reflect, and you can follow the return beam from the standing wave that forms after the reflection. Actually over the complete distance, despite the presence of a gradient in the propagation speed. But the main thing I want to point out here is that in the case of just spatial anisotropy, the propagation speed of light will still be identical in opposing directions. Okay, so far all these different models did not give us what we were looking for. A wave propagation speed that is fundamentally anisotropic in opposing directions, like the one I tried to visualize in this schematic. So how could we achieve this in an elastic medium? Well, we could of course define a different spring constant in opposing directions, but it turns out that if we implement this as a property, we run into big trouble. Here is a hypothetical spring from such a very special elastic medium at rest, and for the wave propagation speed to be opposingly anisotropic, the spring constants must have a different value in opposing directions. Okay, let's just for argument's sake assume that such a spring can exist. This example spring has a spring constant of 2 newtons per centimeter if we pull on it from the left and 1 newton per centimeter if we pull on it from the right. Now let's fix this spring to a weight on one side and have a force act on it from the other side. The energy to expand the string by a distance of x would be equal to the integral over the distance x times the force needed to do this, which is k1 times x. And this means that the energy that is put into the system is equal to the integral, so k1 times x squared divided by 2. However, due to the expansion and the fact that the spring constant is 2 times higher in the opposing direction, the spring starts pulling on the weight with a force that is 2 times higher than the one we have exerted. And this force will now start accelerating our mass. So by the time the spring has the same length again, the weight has gained a kinetic energy that is 2 times the amount we put into extending the spring, and this would clearly violate the conservation of energy and momentum. Just for fun, let's do a simulation and compare wave propagation in 2 different media. To the left we introduce an harmonic vibration in a spatially isotropic medium. To the right we introduce the same oscillation in a medium that has opposing anisotropy in the horizontal direction. The medium only has a 1% difference in spring constant in the opposing directions, but look what happens in this case. We basically observe how the wave amplitude gets higher and higher from left to right, whereas in the other direction, wave energy seems to disappear into nothing. Now, this is not how wave energy behaves, and this is definitely not something we observe in experiments with light. Yet, this type of behavior would directly follow from a difference in propagation speed between opposing directions. It would result in the generation of free energy in one particular direction. So I guess the inconsistencies that arise from a lack of energy and momentum conservation are strong arguments against the existence of opposing anisotropy. Basically, it's in violation of the very fundamentals of physics, because these conservation laws have proven their validity over and over again experimentally and across many different scales. Now I realize that I took quite a detour to arrive at this conclusion. I guess a much simpler way to prove the same point is to look at the relationship between energy and momentum for electromagnetic radiation. Basically, the two are related by a constant, which is the speed of light. So imagine radiation arriving with the speed of light c1 at a 100% reflective interface and then reflect back into the opposite direction. If the reflected light has the same speed as the incoming light, energy is conserved, but if the propagation speed of the reflected light would have a different value, either the total amount of energy or the total momentum would not add up before and after reflection. With the laws of energy conservation covering our backs, you might think that we can safely say that the speed of light cannot be different in opposing directions, and that therefore the value of the one-way speed of light must be equal to the two-way speed of light. However, there is a rather significant difference between the local wave propagation speed in a single point in space and the average speed over a distance between 2 points separated by space. In the first case, the speed of light in opposing directions must be the same due to how energy propagates in an elastic medium. But in the second case, we can indeed come up with a scenario where the speed of light is different in 2 opposing directions. And that is when the light encounters spatial anisotropy on its path that isn't static but a function of time. For example, because of the presence of a temporal variation in the gravitational field caused by a moving mass. If the local gravitational potential changes during the time it takes for the light to make its return trip, light could theoretically have a different propagation speed in opposing directions. But even in that case, we would never be able to measure this.